Mars Mars is the most Earth-like planet in the solar system and the strongest candidate for past or present microbial life. Geological evidence shows that early Mars, over 3.5 billion years ago, had rivers, lakes, and possibly oceans, confirmed by ancient river deltas, lake beds, and mineral deposits that only form in liquid water. During this period, Mars also had a thicker atmosphere and a warmer climate, conditions favorable for life to emerge. Today, Mars is cold and dry on the surface, with intense radiation and a thin atmosphere. However, life on Mars is not expected to exist on the surface but below it. Radar data and lander measurements confirm the presence of subsurface ice and possibly salty liquid water several kilometers underground. These briny waters can remain liquid even in extreme cold, providing a stable environment shielded from radiation. Mars also contains organic molecules detected by rovers such as Curiosity and Perseverance, preserved within ancient sedimentary rocks. Methane has been intermittently detected in the Martian atmosphere. While not definitive proof of life, methane can be produced by microbial activity beneath the surface. Importantly, Mars shows chemical energy gradients, such as iron, sulfur, and hydrogen compounds, that microbes could use as fuel, similar to life found deep underground on Earth. If life exists on Mars today, it is most likely microscopic, dormant, or slow-growing, and hidden deep in the crust where liquid water, chemical energy, and protection from radiation still exist. Mars may not host complex life, but it remains a prime candidate for extant or fossil microbial life. Venus is often called Earth's twin due to its similar size and composition, but it followed a dramatically different evolutionary path. Today, Venus has a runaway greenhouse climate with surface temperatures around 465 degrees Celsius, crushing atmospheric pressure, and clouds of sulfuric acid, conditions that make surface life impossible. However, evidence suggests that early Venus may once have had oceans and a temperate climate for hundreds of millions, possibly billions of years, giving life a window to emerge before conditions deteriorated. The most plausible location for life on Venus today is not the surface, but the upper cloud layers, roughly 50 to 60 kilometers above the ground. In this region, temperatures and pressures are surprisingly Earth-like, and sunlight is abundant. These clouds contain water vapor, sulfur compounds, and trace nutrients that could, in theory, support microbial ecosystems suspended in the atmosphere. Interest in Venus as a life-bearing world intensified after the reported detection of phosphine, a gas on Earth primarily associated with biological processes. Although the detection remains debated and unresolved, it highlighted unexplained chemical activity in Venus's atmosphere. Venusian clouds also show persistent chemical disequilibrium, meaning reactions are occurring that are difficult to explain by known non-biological processes alone. Any life on Venus would need to be extremely acid-tolerant and adapted to aerial existence, potentially using sulfur chemistry instead of oxygen-based metabolism. Such life would likely resemble terrestrial extremophiles found in acidic volcanic environments. If life ever arose on Venus when it was more Earth-like, it may have survived by retreating upward as surface conditions became hostile. Venus demonstrates that habitability can exist in unexpected niches, and that life may persist not on planetary surfaces, but hidden within stable atmospheric layers. Europa is one of the most promising places to search for life beyond Earth. Beneath its fractured icy surface lies a global saltwater ocean, estimated to contain more than twice the water of all Earth's oceans combined. This ocean is kept liquid by tidal heating, caused by Jupiter's immense gravity stretching Europa's interior and generating heat through friction. Liquid water, energy, and chemistry, three essential ingredients for life, are all present. The icy shell covering Europa is estimated to be several kilometers thick, protecting the ocean below from intense radiation at the surface. Cracks and ridges in the ice suggest ongoing geological activity, allowing chemical exchange between the surface and the ocean. This is important because surface ice contains oxygen compounds created by radiation, which may be transported downward and used as an energy source by potential life. Observations have detected water vapor plumes erupting from Europa's surface, implying direct access to the subsurface ocean. These plumes may carry salts and organic compounds, making it possible to study the ocean without drilling through the ice. The ocean floor is also believed to interact with a rocky mantle, creating conditions similar to hydrothermal vents on Earth, where life thrives without sunlight. Any life on Europa would almost certainly be microbial and aquatic, relying on chemical energy rather than photosynthesis. Such organisms could live near hydrothermal systems or throughout the ocean, sustained by dissolved nutrients and heat. Europa's environment is stable over long timescales, increasing the likelihood that life, if it arose, could persist. Europa is considered one of the top candidates for present-day extraterrestrial life, hidden beneath its frozen surface and isolated from the hostile environment above. Enceladus is one of the clearest and most compelling candidates for life beyond Earth. Beneath its icy crust lies a global liquid water ocean, confirmed by gravity measurements and heat flow data from the Cassini spacecraft. Unlike many other ocean worlds, Enceladus actively ejects material from this ocean into space through massive water-rich geysers at its south pole, providing direct evidence of habitable conditions below the surface. These geysers contain water vapor, salts, organic molecules, hydrogen, carbon dioxide, and silica nanoparticles. The presence of molecular hydrogen is particularly important as it indicates ongoing hydrothermal activity on the ocean floor. On Earth, hydrothermal vents support rich microbial ecosystems that rely entirely on chemical energy rather than sunlight. This makes Enceladus one of the few worlds where a complete known energy source for life has been detected. The ocean is kept warm by tidal heating caused by Saturn's gravitational pull, ensuring long-term liquid water stability. The ice shell above the ocean is relatively thin near the South Pole, allowing chemicals and nutrients to circulate between the rocky core and the water. This interaction supplies essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, key building blocks of life. Any life on Enceladus would likely be microbial, living within the ocean or near hydrothermal vents. These organisms could use hydrogen and carbon dioxide to fuel metabolism, similar to methanogenic microbes on Earth. Importantly, Enceladus does not require speculative conditions for habitability. All major ingredients, liquid water, energy, organics, and chemical gradients, have been directly observed. Because Enceladus naturally sprays ocean material into space, it offers a rare opportunity to search for life without drilling, making it arguably the best current target in the search for extraterrestrial life hidden beneath ice. Titan is one of the most chemically complex worlds in the solar system and presents a unique case for potential life. It is the only moon with a thick atmosphere, primarily composed of nitrogen, with methane and other hydrocarbons forming a dense orange haze. Surface temperatures are extremely cold, around minus 179 degrees Celsius, preventing liquid water from existing on the surface. Instead, Titan hosts lakes and seas of liquid methane and ethane, making it the only world besides Earth with stable surface liquids. The surface environment supports complex organic chemistry. Sunlight and energetic particles drive reactions in the atmosphere that produce large organic molecules, which rain down onto the surface. These compounds form a rich prebiotic environment, providing many of the chemical building blocks associated with life. While water-based life cannot function in these conditions, Titan raises the possibility of non-water-based life, using liquid hydrocarbons as a solvent instead of water. Beneath Titan's icy crust, evidence strongly suggests the presence of a subsurface liquid water ocean mixed with ammonia to lower the freezing point. This ocean is isolated from the surface, but may interact with the rocky core below, potentially creating habitable conditions similar to other ocean worlds. If life exists in this internal ocean, it would likely resemble microbial life on Earth using chemical energy rather than sunlight. Life on Titan could therefore exist in two hidden forms: exotic surface life using methane chemistry, or more conventional microbial life within the subsurface ocean. Any surface organisms would be slow metabolizing and fundamentally different from terrestrial life, adapted to extreme cold and hydrocarbon solvents. Titan demonstrates that life may not require Earth-like conditions and that alternative biochemistries could exist in environments previously thought uninhabitable, hidden beneath haze, ice, and liquid methane seas. Ganymede Ganymede is the largest moon in the solar system and a strong candidate for hidden life due to its extensive internal ocean system. Beneath its icy surface lies a deep global subsurface ocean, confirmed by magnetic field measurements indicating conductive salty water. This ocean is estimated to be tens to hundreds of kilometers thick, containing more water than all of Earth's oceans combined. Unlike Europa, Ganymede's ocean is buried beneath multiple layers of ice, possibly separated by high-pressure ice phases. While this makes direct interaction with the surface less likely, the ocean is believed to be in contact with a rocky mantle at depth, allowing chemical reactions between water and rock. These interactions could supply essential nutrients and energy sources, creating potentially habitable conditions. Ganymede is unique among moons because it possesses its own intrinsic magnetic field, which helps shield parts of the moon from Jupiter's intense radiation. This increases the long-term stability of the subsurface environment and reduces the destructive effects radiation can have on organic molecules. The ice shell also provides additional protection, creating a stable, isolated habitat. Tidal heating plays a smaller role on Ganymede compared to Europa, but residual internal heat and radioactive decay may still maintain liquid water over geological timescales. Although the energy availability may be lower, life in deep subsurface oceans on Earth demonstrates that even minimal energy sources can support microbial ecosystems. If life exists on Ganymede, it would almost certainly be microbial and aquatic, hidden deep beneath the ice and evolving slowly in a dark, high-pressure environment. Ganymede shows that habitability does not require dramatic surface activity. Instead, life can persist quietly, protected within long-lived internal oceans. Callisto is one of the oldest and most geologically stable bodies in the solar system, and while it appears inactive on the surface, evidence suggests it may hide a deep subsurface ocean beneath its icy crust. Magnetic field data from the Galileo spacecraft indicate the presence of a salty liquid water layer tens of kilometers below the surface, maintained by internal heat and antifreeze compounds such as ammonia. Unlike Europa and Ganymede, Callisto experiences minimal tidal heating, which means it lacks active geology. However, this apparent disadvantage may actually benefit habitability. Callisto orbits farther from Jupiter, exposing it to much lower radiation levels, reducing damage to organic molecules and increasing the long-term stability of any subsurface environment. The thick ice shell acts as an additional protective barrier. The subsurface ocean is likely sandwiched between layers of ice, but may still interact with the rocky interior below. This interaction could supply essential chemical elements and energy sources necessary for microbial life. Even slow geochemical reactions can sustain life, as demonstrated by deep subsurface ecosystems on Earth that survive with extremely limited energy. Any life on Callisto would almost certainly be simple, microbial, and slow-growing, existing in complete darkness and relying on chemical energy rather than sunlight. The lack of geological resurfacing means that if life arose early in Callisto's history, it could have persisted largely unchanged for billions of years. Callisto represents a form of habitability based on stability rather than activity. While it is less dynamic than other ocean worlds, its protected environment and long-lived subsurface ocean make it a credible candidate for life hidden deep beneath ice, preserved in one of the solar system's quietest worlds.